Okay, so this is the Data Management Best Practices webinar, which is a follow-up to last week's webinar on how to write a data management plan. If you were not able to watch that webinar last week, there is a recording of that webinar, not that specific one last week, but one exactly like it that I did last February. And I will, at the end, I will put a link in the chat to the video of that webinar that I did last February. Today's webinar will also be recorded and it will be uploaded to my website as well, so you can always watch this one again if you choose to in the future. So today's webinar is about data management best practices, which is basically the day-to-day management of research data, and some of the best practices that are generally accepted within in how to manage data. So our outline for today is as follows. We're going to talk briefly about why it's important to manage data well, and then one of the main reasons that we manage data well is for data sharing purposes, and we'll talk a little bit about why data sharing is important. We'll go through some tips and tricks on data entry and manipulation, on how to minimize data error, that is, when you enter data and manipulate data. We'll talk about some quality control and quality assurance practices and best practices, some tips and tricks on how to back up your data, and some ideas on where to do that. And then Joy is going to step in and talk about metadata, and then I'll wrap up with data citation. And I apologize, and I neglected to mention that my co-host today is Joy Penikarucha-Roberts, who is our head of cataloging here in the libraries, and she's going to talk about metadata. She'll come a little bit later and join in and talk to us there. And I will try to monitor the chat for questions, although it's difficult to do that while you're leading a webinar. But I'll pause periodically and check to see if there are any questions. So just enter your questions in the chat if you have any. Why is it important to manage your data well? Well, first of all, it helps keep yourself organized, to be able to find your files and to understand how data was input and how analytic scripts were created, and there's the various outputs at different stages of your analytic process. It just helps you keep yourself organized. Track your science processes for reproducibility, to be able to match up your outputs with exact inputs and transformations that produce them. And reproducibility of research has become a real important topic lately, and data management really supports reproducibility of research. Better control versions of your data. Identify easily different versions that you've produced that can be periodically purged or recreated. You can quality control your data more efficiently when you manage it well. Data itself is a very valuable asset to you and to the university. It's expensive and time-consuming to collect data, and so we want to maximize the effective use of it and the value of that asset. You want to continually improve the quality, which improves your data accuracy, your integrity, the integration and timeliness of data capture and presentation, and relevance and usefulness of that data as well. It helps to facilitate data sharing as well, which we'll go to in just a moment. And last, it helps to ensure sustainability and accessibility of your research data over the long term and for reuse in other scientific research projects. So in summary, the goals of effective data management is to get data that are well organized, both within the files themselves and in the groups of files. Also, that they're documented adequately with metadata, preserved for future reuse, accessible by others for that reuse, and that they are accurate and valid for the purposes that they serve. And if data are all those things, then you will have high quality data that is easy to share and to reuse in science. The data then can then be cited by other researchers, which will add credibility to you, the researcher who prepared them. And overall, it saves time, money, and advances science. So in addition to making your life easier, one of the main goals of effective data management is to facilitate data sharing with other researchers. Grant funding agencies want to see a greater return on their investment, and seeing data collected during projects that they fund get shared with other researchers lets them know that the data is having a broader impact. So let's talk a bit about data sharing and why it is important. Why expend the extra effort to share data? Well, because it benefits the public, the research sponsor, your research community overall, and then most importantly, you, the researcher. How does the public benefit from shared research? Well, the more informed the public is, the better they are able to understand and contribute toward effective public and personal decisions. For example, the public needs data to be able to help with environmental and economic planning. Research data help inform federal, state, and local policies as well. The public can use data to help with social choices, such as who they'll vote for, or how they want their tax dollars to be used, and where they will send their children to school. And last, it can even help them make personal lifestyle choices and health choices, such as exercise and smoking and nutrition. Moving on, why do research sponsors encourage data sharing? Because sponsors have an obligation to maximize the investment of research dollars. Data sharing enhances the value of the research investment by enabling external reviewers to verify the project performance metrics and outcomes. This not only increases the credibility of the data, but also spurs new research that can build upon the initial investment and advance the science rather than duplicate expenditures. The scientific community as a whole also benefits from sharing among researchers. Data sharing allows researchers to build upon one another's work and to further rather than duplicate the science by exploring new findings and combining findings into meta-analyses that cannot be performed with individual data. And in sharing data, the scientific community expands both individual perspectives and the collective comprehension. Access to related research enables members of the scientific community to better reproduce, compare, and assess methods and results. Scientists are able to learn from one another and to educate new researchers as to the most current and significant findings in their fields. And finally, how does the independent researcher benefit from data sharing? When scientists share their data, they gain recognition as an authoritative source and respect as a wise investment for research dollars. When data are exposed, feedback from the broader community can be used to improve the quality and presentation of that data. Shared data also allows for greater opportunity for data exchange and networking opportunities with peers and potential collaborators. So now One of the most important things one can do when managing their research data is to take steps to make sure data entry, processing, and analysis are done in such a way to minimize error. So we'll talk now of ways to do that during data entry and manipulation. The goals of data entry are to create data that are valid or have gone through a process to assure quality, and are also organized to support the use of data and for ease of archiving. Many researchers like to manage their data in Excel, and Excel makes it very easy to use poor data management practices. Excel doesn't enforce any rules on your data entry unless you specifically tell it to. These are data entered into an Excel spreadsheet from a small mammal trapping study. Each block of data represents a different trapping period. You'll see, let me get my highlighter here. So you'll see that this top section is for this date. Then we have a section here which is for this date, and then we have another section here for another date. Inconsistencies in how the data were entered for each sampling period make the data difficult to analyze and difficult for anyone but the data collector to understand. Note the date is listed in different places in each block. And the date is a column in the first block, but it's listed in the header on the block to the right. And inconsistent date formats were also used. In one place, the date is formatted as day, month, year, with the first 3 letters of the month spelled out, while elsewhere the format is a 2-digit month, a 2-digit day, and then a 4-digit year. Note also that the order of the columns is inconsistent. Site, date is in the first block, and then site and plot is in the bottom, the block below that. Then even the columns are named differently from one block to the next. Species is called species in the first block, and rodent SP in the next block. So this can be confusing to any user who must try to make sense of the data, and it would be a nightmare to write metadata for this spreadsheet. There are other problems with how these data were entered as well. Naming of the sites is also inconsistent. For instance, deep well is used in the first block versus DW in the block to the right. And the file contains several typos as well, such as Rio Salado and Rio Salado without the extra A in it. A human can figure out what each of these sites names refers to, but the names would have to be harmonized for a statistical program to use it. And it would be easier to filter for just deep well with a space and not have to know that you need to filter for also deep well with no space. Similarly, in one place, a species code is capitalized PERO, and in lowercase in another part of the same block. Further, in the first block of data, you see that a mean was calculated for the weight of the rodents. The value for that mean, called mean1, is in the same column as the weights of the individual animals. In later manipulations of these data, it would be easy to copy that value as though it represented the weight of a single animal. It's bad practice to mix types of information in one column. It is best for raw data to be maintained in one file and calculations to be done in another file. In addition, you see that there is text data mixed with numerical data in the weight column in the block on the right. You see that it says escaped less than 15, presumably indicating that a rodent less than 15 grams escaped. A statistical program will not know how to deal with text data mixed with numerical data. So what is the mean of 12, 91, and escaped less than 15? You can't calculate such a mean. And to analyze all these data using statistical software and to make it much easier to understand by any user, these data will need to be organized into a column for each variable. Therefore, it is essential that only one type of data be entered into each column and that spellings, codes, and formats be consistent. So this shows the same data entered in a way that would make it much easier to understand and to analyze. The data are not entered into separate blocks arrayed into a single worksheet. They are entered into one table with columns defined by variables date, site, plot, species, and weight, adult and comments that are recorded for each sampling event. The columns of data have consistent types. Each column contains only numbers, dates, or text. And there are consistent names, codes, and formats used for each column. For instance, all the dates are in the same format, and there are no typos in the site names either. Species are all referred to by standard codes. Therefore, if the user wanted to subset the data for species equals PERO, they could easily filter the file for just those data. Additionally, there are only numeric data in the weight column, so a statistical program or Excel could readily calculate statistics on this one column. And preparing metadata for this file would also be much more straightforward. A best practice for data entry is to create descriptive column names without spaces or special characters. Sometimes statistical programs have special uses for some characters, so you should avoid using special characters in your data file. And then when it comes to file naming, for instance, a file named fieldvisit1 underscore small mammal data underscore 2010-0411.csv indicates that this file contains data collected during field visit 1. It contains small mammal data, and it is version dated April 11th of 2010. We know that it's April 11th and not November 4th because they're using the standard ISO date format, which is always a 4-digit year, followed by a 2-digit month, followed by a 2-digit day. And this name is much more helpful than the file named mammaldata.csv. Another issue with data entry that you want to be aware of, there's a lot of things great about spreadsheets, but one must be wary of problems that can arise from their use. Spreadsheets, for instance, can sort one column independently of all the others. The data entry person for the upper spreadsheet elected to leave empty cells for the variables site, treat, web, plot, and quad. It's obvious why, and it doesn't cause the human reader any problems. But if someone happens to decide to sort on species, for example, then it's no longer clear which species maps to which time period or to which measurements, and this could make the spreadsheet unusable. So it's always a good practice to fill in all cells when using a spreadsheet for data entry. A best practice is to enter complete lines of data so that the data are sorted on one column without loss of other information. When you collect data, you're bound to have some data points with no values. and there are ways to ensure that those values are consistent and don't throw off your analysis. A preferred way to identify missing data is with an empty field. If for some reason an empty cell is not possible, for example, the software you're using requires something to be there, then use an impossible value such as 9999 in a numeric field. And in text fields, use NA for not applicable. If you need to explain something, you can use data flags in a separate column to qualify empty cells. For instance, in this example of stream chemistry data, the flag M1 indicates that the sample was not collected at that interval. Likewise, the flag E1 indicates that the value was an estimated value. As mentioned previously, Excel is a very popular data entry tool. It allows you to enforce data validation rules. Here you see a drop-down list has been generated that allows the user to only select entries from a list. In this way, only defined species codes get entered, and the data are consistent. And you do that by using the data validation tool, and the validation criteria would be a list. You create the list, and then your cell will include a drop-down list, and you can select from a list of predetermined values. And that cuts down on typos when someone has to enter the values by hand. Here's another example of data validation using Excel. The height variable has been defined to contain only values between 11 and 15. But when 20 is entered, the user is told that they have entered an illegal value. So this is another tool that you can use within Excel to force Excel to ensure that only specific predetermined values are entered, or values within a certain range of numbers. Some researchers are turning to database software instead of spreadsheets for their data management needs. Databases are a powerful option for storing and manipulating data sets. Here we list some of the pros and cons of spreadsheets versus databases. And some of the databases available include software such as Oracle, MySQL, SQL Server, and Microsoft Access. Spreadsheets are good at making charts and graphs and doing calculations. They're also very easy to use, but they can become unwieldy as the number of records grows and the dataset becomes complex. Databases, on the other hand, work very well with high volumes of data, and they are much easier to query in order to select data having particular characteristics. They also maintain data integrity. That is, one column cannot be sorted separately of the others, as is the case with spreadsheets. Databases also enforce data typing, which is a best practice. This means that only data of type text, for example, can be entered into a column of type text. This helps prevent data entry errors. Databases do have a steeper learning curve, however, than a spreadsheet, such as Excel, but there are many benefits. So I would encourage you to look into learning a database software if you don't already know how to do that. A relational database matches data stored by using common characteristics found within a dataset. This helps preserve data integrity and also makes it possible to flexibly mix and match data to get different combinations of information. A database consists of a set of tables, and each table has a defined relationship with another table or tables using a common piece of information called the primary key. Databases also have a powerful command language for querying and manipulating information called Structured Query Language, or SQL. Here you see a dataset for plant phenology has been divided into 3 tables. one describing site information, one describing characteristics of each sample, and one describing the plant species found. Relational databases are currently the predominant choice in storing data like financial records, medical records, personal information, and manufacturing and logistical data. Database features includes explicit control over data types and has the advantages of quality control and performance. Here in the plant phenology table, only dates are allowed in the date column, only text is allowed in the site column, only real numbers are allowed in the height column. And then if a user tries to enter a question mark under flowering, the database will reject the entry because it only will accept a Y or an N for yes or no. This is useful for defining how data is to be entered. Relationships can be defined between two sets of data, or in this example, between two tables. Suppose that you have two tables used in the plant phenology study, one for observations and one for sites, and you want a third table that contains both observations and the latitude and longitude of your site. Because both tables contain the site information, they can be joined together to create a table containing just the info you want. Database features also include a powerful command language called Structured Query Language, or SQL. These are just a couple of examples of what you can do with SQL. The table at the top of this slide is named soil temp in the database. The first example SQL command returns all records collected on February 1st of 2010. The second select statement returns all records from the table soil temp, where treatment is in and sensor depth is 0. From this example, you can get a sense of how easy SQL is to use to subset data within the tables based on specific criteria. This is only very simple SQL. There is much, much more that can be done with it. Forms can be created to make entering data into a relational database as easy as entering it into Excel. The screenshot that you see here shows embedded forms that were created very quickly using Microsoft Access for adding data to 3 tables in a database of plant cover measurements. To summarize, be aware of best practices when designing data file structures. Choose a data entry method that allows validation of data entered, and be sure to invest time in learning how to use a database, especially if the data set you're collecting is large or complex. Okay, so now you've taken steps during your data entry process to minimize the possibility of data error. But that doesn't mean you need to stop there. There are other ways to help with quality control as well. In general, there are 2 types of errors that can occur in a data set. First, errors of commission are the result of incorrect or inaccurate data being included in the data set. This may happen because of a malfunctioning instrument that produces faulty results, data that are mistyped during entry, or other problems. And on the other hand, errors of omission are the second type of error. These result from data or metadata being omitted. Situations that result in omission errors are when the data are inadequately documented, when there are human errors during data collection or entry, or when there are anomalies in the field that affect the data. The remainder of this module will cover some best practices for quality control and quality assurance for the different stages of a research project. First, before data collection, a researcher should think about defining and enforcing standards that will be used during the project. Consider formats that will be used for the data tables or data entry forms. Also, if abbreviations or codes are used, they should be defined up front. Measurement units should also be specified, and relevant metadata should be identified before collection. Second, you should assign responsibility for data quality before collection begins. Ideally, the person responsible for data quality assurance and data quality control is the person collecting the data and is educated in quality control and assurance methods. Consider using techniques that help eliminate mistakes during data entry. Examples are using double data entry, where non-digital data are keyed in by two people independently. Differences in entries can then be detected via computer programs and eliminated further for mistakes, or examined to eliminate where the mistakes are. Another way to reduce data entry error is to record yourself reading off the data and then transcribe it from the recording. You may also use a text-to-speech program that reads the data to you while you type it into the computer. If you are using spreadsheets or databases, you should carefully consider their design before and during data entry. Use consistent terminology within the database and atomize your data. This means only one piece of information is in each cell of the spreadsheet. Multiple pieces of information embedded in a single data cell will be problematic during data analysis. If you are using a database, restrict what can be entered into the database. For example, set up a field to accept only text or only numerical values. Choose a maximum number of characters or a range of values a field will accept, or set a field to accept only unique values. Finally, document any changes that you make to the data. It saves time if good records of data editing are kept, since multiple users are less likely to spend time on error checking with old versions of data. If mistakes in data editing or cleaning are made, good data records will allow these mistakes to be undone easily. Documenting data changes may be as simple as creating a text file to accompany the dataset, or it may involve using a scripted program for correcting errors so that each step taken is clearly documented. Once data are entered, basic quality assurance measures can be taken. First, if data are in spreadsheets or databases, be sure that they line up in their proper columns. Also, check for any missing, impossible, or anomalous values. One way to check for these problems is to sort data fields and check for discrepancies. It is also often useful to perform basic statistical summaries, such as means and standard errors. If data transformation was performed during analysis, compare the statistical summaries before and after transformation to ensure no mistakes were made during that transformation. Another strategy for quality control after data are entered is to look for outliers. Outliers are extreme values for a variable. Extreme values are those that lie outside of the statistical model being used to create the data. Keep in mind that the goal is not to eliminate outliers, but to identify potential data contamination. An easy way to do this is to plot your data on a graph. In this graph, most of the data fall along the black line. The outlier identified with the red arrow should be flagged for further investigation. You may find that the data point is legitimately correct, in which case you want to keep it. But you may also find it's the result of a typo when you entered the data, in which case you would have the opportunity to correct it before it messes up your analysis later. One common strategy for identifying outliers is using graphical methods. For instance, normal probability plots, regression, as in the previous slide, or a scatter plot. If data are geographical in nature, mapping the points can be helpful to ensure latitude and longitude were correctly entered. This map shows an example of an error that is the result of misentering latitude data. Another method for identifying outliers is using statistics. You can look at the deviation of a value, which is the difference between the observed value and the mean of that variable. By subtracting values from the mean of the dataset, the presence of outliers or faulty data can become apparent. During this tutorial, we first defined several concepts important for understanding quality assurance and quality control. This included data contamination and the types of data errors that can result in poor quality data. Then we covered best practices for quality assurance and quality control. These strategies prevent errors from entering a dataset or identifying those errors if they are present in the data. It is important to define and enforce quality assurance and quality control standards before, during, and after collection and entry of data. Now you've made sure your data were entered properly, and you've cleaned up the data from errors of commission and omission. All that hard work could be for naught if you don't have a good backup plan. The main difference between data backups and archiving is that backups deal with data that is copied elsewhere and potentially can be overwritten again as the data change. Archiving makes a record of data that is usually in its final state. When a user performs a backup, they are in essence taking a snapshot of the data at that moment in time. This allows the user to restore the data file as needed, such as when the current version of the file is corrupted, lost, or somehow destroyed or altered. Backups are often used for short-term storage or near long-term storage, depending upon the user's backup needs and procedures. Backups are usually scheduled on a frequent basis. Archiving, on the other hand, deals more with records that are no longer in use and is used to create a historical snapshot of the data. This provides for preservation of the data for future needs. Usually, archives are made when a project ends or when appropriate. Regardless of whether you are dealing with backups or archives, you should have multiple copies in case one or many versions fail. So there are many reasons to perform backups, and they include to mitigate or prohibit the loss of data, which may or may not be reproducible. You also want to save time, money, and productivity, as little to none of the data will have to be reproduced. Having a backup already in place means you are prepared for when the unexpected happens, such as human error, disasters, or computer failures. It allows you to go back to earlier versions and see what your results were. For example, if you are creating models and used data from an earlier model to run, the most recent file you have on your computer may not have the same data as when you first created the model output. It also provides for the ability to send older files to others, regardless of the current version or the state. For example, if the current version has been corrupted. And then last, it may allow you to respond during times when you're questioned or when the results are questioned. Those results were based on older versions of the files. For example, you may find that you will have to justify your results in court or to other scientists. By having access to older files, you may be able to respond to their requests for information. Or you may not be able to reproduce the data, and the original copy may be the only evidence of the data collection. Our last topic covers data preservation. Data preservation is a comprehensive topic. which includes things such as backups, archives, data conversion, reformatting, and rescue. Data rescue deals directly with older files that may no longer be a format that is easily accessible and will require some rescuing before it can be used again. Data rescue becomes more and more important as projects end, even if data was being preserved throughout the lifetime of the project. Often files go untouched or orphaned. Frequently, data has not been managed properly and requires that some form of data rescue be performed so that the data isn't a total loss. So when preserving your data, you need to consider many things. Data formats. It is best to use non-proprietary and standard formats. This will better ensure readability in the future. Be sure to check files after converting them, as data, metadata, and formatting loss can occur. With regard to file versioning, make sure to use some sort of naming convention, such as incremental letters or numbers, to keep track of file edits and revisions. This will also help you to more quickly locate the correct version of a specific file. And then with regards to naming, use file names that are consistent, descriptive, and concise. Many software programs use a generic file name as their default file output, and usually these names are too generic to be useful. Here's some examples of some file names. You see the one in red, file name underscore 120413, is a bad file name because you don't know whether or not that date is April 13th, or I'm sorry, is April 12th or December 4th. And so you want to use the standard ISO date format, which is a 4-digit year, dash 2-digit month, dash 2-digit day. And so that file name in the middle is better than the first. It is very clear that you're speaking of December 4th of 2013. Now last, you can also add the date and time zone to your file name if that is necessary, and the ISO standard allows for that. And so you see that on the last example, you can get very, very specific. So with regard to best practices for backing up, the first best practice is to create a backup plan. And this may be a physical document or a web page or listed in someone's job description. Regardless of how you create it, it's important to address any of the previously mentioned issues and concerns. For example, who do I contact when I need to get a copy of a file off a backup? I've included a data backup and security checklist, which I will send to you via email as a handout for you to use to create that policy or plan. Once you have a backup plan in place, it is good practice to review it periodically to ensure that the information still has value and is applicable. Hardware, software, projects, and staff can change over time, so you want to make sure that you update your plan as needed. And as I mentioned, I will send you a copy of the data backup and security plan via an email attachment after the webinar is finished. We'll now move on to the metadata section. Joy is going to take over and talk about metadata, and after metadata, we'll have one more section talking about data citation. Joy, I'm going to go ahead and let you take it from here.
Okay, can you hear me?
I can hear you, yes.
Okay, thank you. So, good morning, everyone. My name is Joy Roberts. Let's see if I can move. So, even though it say the remote control doesn't seem to like me too much. Let me see if I can. Oh, here we go. So, my name is Joy, and I'm head of cataloging. Today, I will be talking to you about the metadata. And the best way to contact me is to my contact information here, and especially on the email, since I do go to meetings quite often. So what is the metadata? As you have heard from Chris before about different things you have to do to back up the data, versioning, all of that information can be reported in your metadata creation. And that metadata is also a way to document the data for the future discoverability, shareability, findability, and also reusability for now and in the future. Metadata can have many kind of elements, especially for the information on who, what, when, where, and how, and why the data were developed. And also it can be used to preserve the usefulness of data over time by detailing methods for data collection and dataset creation. And metadata also greatly minimize the duplication of efforts in the collection of expensive digital data and foster the sharing of digital data resources. You have seen metadata in your real life, but you may not know that's what they are. When you listen to music in iTunes, if you click on the get data section, you can see that you can have the songwriter, the singer, all the music list, and that's a part of metadata for music. Nutrition label is also have metadata to tell you what cholesterol, sodium, what elements you have in as nutrition. In the library world, you have seen the catalog, and that's also metadata. We have the information on the author, title, creator, publisher, and subject, and format. And you will see that also when you create your own metadata for data sets. So why do we need to do all of this work for data sets and for the future? As you can see, all of these elements I put on the screen here, you may have the knowledge or the data now, but your data integrity can deteriorate over time if you don't capture the information now. So now is the best time. Now meaning the time that you are working with the data set is the best time to collect and develop this metadata for your data reporting. And over time, with the hackers and other things like that, and also technological change, your format and the application that can be used for your data will also be changed over time. So versioning, documenting the app, the methodology, the tool software you use is also important for preservation and migration. In metadata, to be able to not only create your own metadata, but exchange with the others and also have the computer to manipulate and preserve your data, we have a community of standards, and there are many kinds of standards I will be talking about. The standard provide you with the common terms, definition, and structure that allow for consistent communication, for data exchange, but also for the computer to manipulate and use it as a search engine. And later on, you can see that this same data set or data points can be used for data visualization. Here is a very universal metadata standard called data site metadata schema. You can see that there are very common elements, not disciplinary specific. So anyone in any discipline can use this type of metadata scheme. You can see that besides the general knowledge of general information like title, creator, you also have very specific information like rights, versioning, or the funding agency that's specific for data sets. And I want to mention that this data size has been used wide in the worldwide. And one thing about data science that it creates a DOI to help you preserve your data on the long term. And it's been used by the European Commission for their open science platform called Open Air, and another Zenodo, which is a universal data repository created by CERN, or the physicists that study the Large Hadron Collider in Europe. So it's been a well-known and very popular metadata for any discipline at all. So this is an example. When we get into more discipline specific, the metadata also change. This is one of the example of the in the very discipline specific metadata on the North American Breeding Bird Survey. So besides, you can see that besides citation and other general information, you have the abstract section that describe the methodology, how the data were collected, and in the purpose section for the rationale of the research. This is another example of the discipline-specific database for dataset. The Pangea database is for the earth and environmental science, and it has a different requirement for metadata that tailor to the discipline. So for example, you have the metadata elements to describe the ocean drilling dataset with the expedition location by latitude and longitude, for example. This is the example of one of the data set in Pangea. You can see that the metadata are used to describe the data, but the facet and filter also used for linking to other research projects. So the data point become the search point for the computer retrieval as well. So this is the data set from the deep sea drilling project that process the smear slide data and derive directly from the smear slide data collected on board the ship called the Global Challenger. So in the metadata, you will have the ship's name, expedition's name, the events with latitude and longitude, and location in the ocean, the size of the drill core, and the parameter or the physical property of the rocks and sediment collected. And this metadata, as you can see, when you go live on this record, I put the link to it. You can play around with this later. When you get to the mineral area, it has a search hourglass. You can click on that and can link, so you can find the quartz or volcanic glass that can be found in the Pangea database from different projects as well. And you can see that the information is used for data visualization. The map here on the corner of the screen has been using the geolocation to project the map for you where the location of this project is. Another thing about your data set is that nowadays, most of you may be aware of something like ORCID or the researcher ID, Scopus, and other kind of different researcher ID. You can now add your data citation in the ORCID account, and it will link back to the database. For example, Alice Lefebvre here, one of the researchers, has her own ORCID ID, and she add this data set in ORCID that link back to the Pangea database. So there's a lot more interoperability between your researcher IDs platform to different data set platform as well. And this is very much a normal practice among the database now to facilitate the researcher IDs. In your At UT, you have pivot for your funding opportunity database and also elements for your faculty evaluation. Your ORCID ID would link um, to your pivot and also in elements. And for pivot and ORCID, they have an agreement to update the data in real time. So when you update your ORCID ID, it will go into pivot account right away. Another thing, like I mentioned earlier, your metadata can also become a visualization. And there are many, you can use it for data visualization. There are some examples here I add. One is the Place and Space, a project at the Smithsonian for scientific data visualization. Carto is a mapping tool that you can use for putting your data on the mapping application. There's also the book by Kathy Bonner, who's the project coordinator for Place and Space at the Smithsonian. And you can see different projects that use the data set to visualize the data. And also in the geospatial humanities, you can have something from your digital humanities and map it on the format for the data visualization. I add a project by a colleague from the American University of Beirut here as an example. Dr. David, my colleague, studied linguistic landscape of Beirut. He would use the application called Fulcrum to take the photo of the site that has different signage, and then he would add the metadata and project that metadata on the map of Beirut, and you can even pop up all of these elements you can see in the color can pop up and show you the metadata. I try to progress. Okay, here we go. So the next example is an eBird data. This is from the Cornell Lab of Ornithology in Ithaca. But they collect the data from bird observers worldwide, and this is an example of how metadata from bird observation can be used for visualization. You can search this website and you can get the map that based on the Tennessee birding hotspot for the blue heron during the months of March to May last year. So all of these are different metadata elements that you can configure and really put it on the map by these facets. I put the additional resource if you want to look for other disciplinary metadata. This site is great that it has different discipline, but also show you different standards that belong to this discipline and also use cases and also different tools you can use for your data set and to create your metadata. So that's it for my section on metadata. If you have any question, you can find Chris and I through our contact information. Thank you so much for your attention.
Thank you very much, Joy, for talking about metadata and all its many useful purposes, including data visualization. We're going to go into this last section on data citation, which will conclude the webinar today. Data citation is similar to citing a published book or an article, which is what you would do if you write an article. You would cite any work that you use the same way you would do the same with research data that you might reuse as part of your research data. It's always it provides the information that's necessary to identify and locate that work. There are no established standards yet on research data citation. However, many journals or data repositories or even professional organizations may have recommended formats that you can use. This is an example of a data citation from the Dryad data repository. You see that the first part is similar to citing an article. You have the authors. In this case, these are the people who collected the data. You also have the date in which the data were collected, or at least the data, the date that the data were finalized and published. The title of that data set is typically named as data from, and then usually the name of the article or research project name that the data were from. And then the publisher is PLOS ONE in this case. And then last you see a DOI, which is a digital object identifier, and anyone having that DOI will be able to locate that exact data set by just by clicking on a link like that, or by resolving that DOI within the DOI website, that dx.doi.org website. So that concludes our webinar today on data management best practices. Before I leave you, I wanted to give a plug for the group in the library called the Scholars Collaborative, which is a group of specialized librarians who are here to help you with different research needs. We have Rachel Caldwell, who is our scholarly communication librarian. Her role here is to help you with any issues related to publishing or copyright. If you're interested in publishing in open access journals, she would be the person to talk to find the best one. And also, if you're interested in learning more about predatory journals and how to avoid those, then she can also help you with that. I'm the data curation librarian, and I'm here to help with making sure that you have a good data management plan written for your grant proposals, and also that you are able to meet the public access requirements for data management and data sharing and preservation. Eric Arnold is our GIS specialist. If you have any need for geographic information systems or mapping components within your research, then Eric will be able to help you with that if you need help. And then last, Michelle Brannon is our media literacy librarian. And if you have any needs for audio or video editing, or some graphics or anything related to that regarding your research, then Michelle would be the person you need to contact for that. So I thank you for attending today's webinar, and we are here to help you if you have any additional questions about anything we discussed today or anything regarding data or metadata. Please contact me or Joy at our contact emails here. I'm also able to help with data management plans, locating data sources, and helping find the appropriate data repositories if you need that help. So that concludes today's webinar, and thank you very much for attending.